for the introduction. Also, thanks for this event, and I'm happy that you accepted my self-invitation to speak here. The NewAthena observatory, the mirror. First, I would like to introduce our company. So we are biking distance away from here, 20 minutes roughly. In the Netherlands, everything is biking distance, but it's really biking distance. We are a highly international team of 75 people, and we work, 35 people of us work in high energy optics, so building this mirror, parts of the mirror. Then there's remote sensing that make cameras that see lots of colors, and they take pictures of the moon and asteroid and Mars. And we also have a branch which is inspection systems. They make measurement systems for example, agriculture. I also remember that slide from Jelle, the second slide. I also have one, which is why do we want objects? We heard about black holes, also neutron stars. Every time things fall in, there's nuclear explosions and X-ray come out. Supernova explosions as well, but also large structures in the universe where there's a lot of hot gas that we want to understand. And more things. So, every time I read about the proposals of astronomers, what they want to do with this, I see pictures like this, and so basically, NewAthena has two detectors and a big mirror, and the two detectors, one of them is WFI, that has a large field of view, so it can take snapshots of this X-ray sky quite fast, so that it doesn't have to integrate so long. So you get an overview like this with lots of blobs of X-rays, and then there's another detector, which is the SciFu, and it's also cryogenically cooled, and it has a really high resolution in energies. So what I imagine astronomers would then do, take a large snapshot with this WFI, see lots of parts, and then they zoom in like in the CSI movies where they enhance, and they take spectra like this with lots and lots of lines, these fingerprints that Jelle was talking about, and then they would come and say, okay, let's zoom in here this block, a galaxy cluster with such a spectrum. Let's publish it in Nature Astronomy. Then the next time they zoom in here, see more lines of black holes, and then they get the science publication. And so it goes on and on. So it's going to be lots of publications from this instrument. To be able to do that, they need to have lots and lots of photons collected in the mirror. So that's what I will talk about in the coming 15 minutes. So here we see again a render of this telescope. This thing will be 2.5 meter diameter, and it looks very interesting. Actually, I brought from my colleague, he basically printed a model, 1 to 5 of this object. It's divided into petals, and then you have lots of these small mirrors in the mirror modules. And this image, this picture shows you like the size. You know, engineers from Esron visited us the other day, and they brought this poster with them. And my colleagues and I, we worked there for a couple of years already, and on this project. But still, when they brought just a piece of paper and life size, we were standing around there for minutes and discussing how big this thing actually will be. So quite cool. So now I will spend some time explaining why does it look so funny and how do you actually make an X-ray telescope. First, normal Cassegrain telescope. You get to take a primary mirror, which has a certain shape, parabolic shape. Then a secondary mirror with a hyperbolic shape. And when you collect normal photos, visible photos, they bounce off, and then you get a focus spot. But X-rays, they get absorbed by quite a lot of things, and it will be like throwing a rock in the water. So what you would have to do is, instead of just throwing the rock, you flip the rock, and that's what X-rays do. If you take the mirror and look at it at the shallow angle, you will get reflection. The second thing, if you have a rough mirror, that will scatter a lot of photons around, so you need really a very smooth surface below 1 nanometer roughness. And secondly, you also make some coatings on it, and it will reflect much better than just any surface. So back to the telescope cartoon. To build such a telescope for X-rays, you take this design, the Cassegrain design, you draw out these mathematical shapes, parabolic primary, then the second one, secondary mirror, hyperbolic secondary, and then you have to go all the way out on this, you don't make the mirror over here, but you go all the way out here and set some mirrors, 2 mirrors, and the X-rays bounce off to the focal point. Unfortunately, this gives you only a very thin shell of collecting area, but that's too little. So you make many of them, nest in each other, like onions, cut open onions, that's also rings. And then you have a lot of collecting area. And 2 prime examples. So in the quiz you heard about Chandra. There's also Exmon Newton from the Europeans. Both were launched in 1999. And they really look like this. Here Chandra's mirror is solid glass that they polished from the inside a lot. And so that has really good resolution, this telescope. But as you can see, you can't make so many of these mirrors in each other, so the collecting area is not big. And the Europeans did the other thing. They made a lot of thin shells out of metal and put them into each other, so you can get lots of photons, but as soon as you start mounting these shells into the structure, they warp a little bit, so the resolution is not as nice. And so now, in 11 years' time, we will have this mirror, which is this object just 5 times bigger, and it also has shells in it, but these shells are made of silicon wafers, because silicon wafers, they got to be really nicely polished, because you want to make nanometer structures of them, like transistors and so on, but we use them to make X-ray mirrors. And the way it works is, so this German company is Siltronic, they grow these single crystals, ingots, cut them with a blade to these, and polish them to these wafers. They are that big. And then you can, the problem here is that you can't make a cylinder out of it because it's a pizza-sized disc. So what we have to do is cut them up into these rectangular plates, and also you cut some slits in it so that the photons can travel through. And I brought 2 of these. I sneaked them out of the clean room. I will pass them around. You can have a look. On the back you will see these pores that we built in, or the company that we work with. They are in the east of the Netherlands, it's called Micronit. They cut these things into shape. And then the second step, what we need to do, as I explained to you before, we need to put some layers on it, metal layers, to enhance the reflection. So the second plate in this box, it has this metal pattern. We have this large machine, and a year ago when we moved the buildings, as you said, I moved a lot of equipment. We also moved this thing, and I was sitting in a meeting and I looked outside of the window and it was hanging in mid-air. This €1 million machine was hanging mid-air on a crane. That was the interesting sight. But now it's in the new building, back in working, and it has platinum and chromium and carbon as targets. We put lots of plates in it. And then there's a drum where the plates are, these carriers are hanging, and it goes across this purplish plasma, and the plasma contains the metal ions, and then they bombard the surface and stick there. And if you want to, so we make it one layer, and then that is already good enough to increase the reflectivity. But if you want to have the 6 kV iron peak, we are working to put many more layers on it, so multi-layers. You put first a layer of platinum, then a carbon, and then another one. So this thing rotates the whole day until you get enough layers to enhance the little peak of this famous iron line that you saw in the previous talk. Next step is also important. You put all these plates in a carrier, put them in the so-called wet bench, and it's basically buckets of chemistry, and the robotic arm goes down this carrier one by one. And what you do is clean the plates off from particles, but also you activate the surface. This is an important step for the next one. We put OH groups on the surface of the silicon wafer, and what makes the surface hydrophilic, so a couple of water molecules stick to the surface. Intermediate step is stacking. Almost final step here at cosine in the Netherlands. We use these stacking robots that you see, one of them here. It's an automatic machine. There's a robotic arm picking each plate and processing it. And the process is like this. We first have a master shape, it's called the mandrel, which is precision polished, and it has the right subscription for the X-ray optics, so the right radius, the right angle, and things like that. And the robotic arm puts the first plate on it, upside down. It's upside down because it needs to mimic the surface really well. And then comes another plate on top with rib side down, and then you have these OH groups with water, and it actually sticks to each other with the help of these OH interactions, van der Waals interaction. And you do this many times. After 4 hours, you have 38 plates stacked on this mantle. And also, I made an animation how it works. And I also brought another goodie to look at. That's how a stack looks like. And yeah, just that. Okay. So at cosine in the Netherlands, we are busy with developing this whole process from getting the wafers down to getting the stacks, and we also have different radii as you see in the model and here in this picture. You have the outer ring, the inner ring, and the row 8, it's called, this one. We develop all of them in parallel, but this one is special because we had a couple more years experience with it, and we actually gave it to a pilot plant where technical staff, they just basically make 10 of them a week to get some statistics how well that process works and things like that. And in parallel, now we are starting to develop, we have 2 engineers, and they make all the designs for this row here, 13, and number 3. And then as it goes, we will build it up and make, in the end, we have to make 6 iron mirror modules made out of 2,400 stacks, and we need to process 90,000 silicon wafer plates to make this mirror. In the last few minutes, I want to talk about what happens with these stacks, because you're not done yet. One stack is just a lot of one of the surfaces, for example, hyperbolic or parabolic surface, the primary or secondary. So you need to put them next to each other for the X-ray to be focused. And we do this at the synchrotron in Berlin or Spain. Synchrotron is a large circular donut building where you accelerate electrons in the tube, in the vacuum tube, and every time they bend around the magnet, X-rays come out. And you want to, firstly, we want to align the 2 stacks in respect to each other in such a configuration. So you first glue one stack in between two plates, we call them brackets, put them into the synchrotron tube, so in the beamline, and then you put another stack next to it, shine the X-rays and see 12 meters, because that's the focal length of the telescope. 12 meters behind you see a focal spot that you are aligned perfectly, and then you glue them in place and take the mirror module out. And one bonus from all these beamlines is that we also get data from them to characterize how well the performance of such a mirror module is. And once we get the data, we publish it and go to conference and say, okay, here, astronomers, we are still on track, we are giving you optic that has this focal spot, a very tiny one, and half of your photons will be in the pixel of this cryogenic detector, and taxpayers' money is well spent. And we do it also at different energies, just to mimic what will be then detected. That I already had. And so yeah, that's basically it. So thanks for listening. We are just 25 minutes from here. We make these objects. And thanks for listening.
You mentioned at some point that you have two engineers that are working on the third and the 13th row. But what's the difference between them? And why do they need to work specifically on one row at a time?
So the question is why do we have engineers to work on these different rows? Firstly, they look different from each other because if you are 12 meters away and you look at this mirror, the incidence angle will be different. So in the inner rows, you will look more shallow, so you will look more through these things, and so they are longer to capture all the photons. And out there, you have a higher, steeper angle, so they need to be shorter to not block the light from your high incidence angle. So they look, all of the 15 rows look different. And we also need tooling to process all of them. You need this special, what is this thing? The mandrel. You need 4 mandrels per mirror module to have the different radii and different angles to kick the photons into the detector. And basically all the processing tooling, the stacking robots need different grippers for gripping the plates. They're wider or shorter depending on the radius. Yeah. And it takes a couple of months to design a whole row. Yeah.
Thanks a lot, very interesting. Imagine for 1 minute that I wanted to buy one of these modules for my living room.
Yeah.
Do you have an estimate of the cost?
Well, the whole mirror is just it's a fraction of the whole telescope. The telescope costs roughly 1 billion, and this thing will be 130 million. And so divide that by 600, and then yeah. Yes. So don't drop this whatever. Yes.
Thanks for the interesting talk. Does the coating deteriorate with time? And if so, is it like a limiting factor for the mission, or is it something else?
Not supposed to deteriorate. We have platinum, which is a noble metal, so you can even place it in the oxygen atmosphere and then won't degrade. On top of it, for the low energy X-rays, we have carbon, which could absorb some oxygen when you store there. But in orbit, you have these high energetic protons and also small meteorites that could damage the optics in the end. But I think for the lifetime of the mission, it should be okay. And there's active research going on how true what I'm saying is. Yes.
I'm just wondering how heavy the whole mirror is going to be.
Oh, that's actually I don't know myself. I have to look it up. But it's definitely light. That's the selling point of this technology, because you make it out of silicon wafers, and it enables it to make it big. These other things from the golden days, they are way, you can't make them that big. It will be too heavy. These two different mirrors. Yeah, they're much smaller. Yeah, you have another question.
If you produce the module, you are testing each module, right, at the synchrotron?
Pretty much. We actually we have a whole chain of facilities. We have the Bessie synchrotron. Then there's another next door to it. We will build a smaller version of a X-ray source that it's basically a hole like this, but it has a regular X-ray source, like you shoot electrons at the target, and then you try to collimate them as well as possible, and then shoot them through this mirror module to see how big is the focal spot. That is a facility that is being built. Then there's another one in Italy that is being built. It's the Vertex facility, and that is going to be. Actually, I have a backup slide. Luckily, so this is how you make this aluminum structure. Some kind of 3D printed process, or it's a big aluminum disc that they milled out, and they has all these pockets for the modules. And then there's this Vertex facility where you put it first in one chamber, put the mirror module in, shine some UV light in, and see if everything is aligned. And then there's a rail going into a vacuum chamber, and down there's an X-ray source on a gantry that you can move. And 12 meters in this vacuum tower, there's a detector that picks up how well everything is aligned and how good the mirror modules are. So, a couple of steps of testing along the line.
I was wondering if you're making just one, or if you're also making one just in case the knowledge.
Yeah, we have money for one, I think. But so on paper, wait, why is it not? Is it in presentation or because I can't? Oh yeah, okay, thanks. So this 600 is a little bit too much. There's a couple of them for like 100 or so for qualification, if everything is all right with these objects, and then the rest will be actually integrated. But then if it blows up in the rocket, then I don't know what will happen. That will be very sad. That's for sure. Yeah.
So that leads to my naturally to the next question. So I was wondering, how are you mechanically making sure that these things stay robust, and also at the module level and also the whole integrated level?
Yeah, at the module level, we are supposed to, each time we make one, we go through qualification testing, where you have like a machine that is just vibrating. You bolt it on this table, and there's compressed air that's vibrating this whole thing with different frequencies, and you see if it's kind of stays intact. You can also shock it with a hammer, with a calibrated spectrum, not just a regular hammer, but a special hammer. And then I think the whole structure also needs to undergo these tests, but not. I don't know.
I have another question regarding like the response of these like mirrors with the beam of the synchrotron. Like you had a slide with different like
Point spread
incident
functions.
radiation strands. Yeah. So is this like, how should I interpret this? Is it related to the PSF of the actual instrument? Is it going to be so weirdly behaved, or once you get all the mirrors, then it's going to be kind of well behaved?
Yeah, imagine you just have one. This is a point spread function at 1.5 kV of one mirror module, and it's just one row. So you need to have like all of them of one row azimuthally aligned, and then you get 1, 2, 3, 4, 5, so like a little star going around. And if you add even more, then it averages out to some shape, which we don't know yet, but it will be something
And
brownish.
total and what's the difference between total?
70%, 100%.
Yes, no, here 70, it's the inner, actually we cheat, we actually make 30 rows, and we cram 2 rows in one, and we call it mirror module. And so, yeah, this top one we call the inner X-ray optic unit, and the bottom one the outer X-ray optic unit. And we make them separately in the separate stacks and put them in one mirror module. And this top one is the E XOU and top lower O XOU. Yeah.
I'm sorry, I'm so not familiar in astronomy things, but I had just a really simple question. You talked about taxpayers' money. Who is paying for it? Yeah. For example, this 1 billion NewAthena thing, and it's international. Like how does the funding work? I'm just.
It's a very good question. We are funded by the European Space Agency, and they get some negotiated income from the different member states. And so then there's a science department at ESA that says, okay, we need to develop this technology here. Is the money. Yeah. Some of it. Oh yeah.
Yeah, maybe a broad question. What was the biggest challenge for constructing such a mirror?
Where should I start? Like in last year or?
Just in general, what was the most difficult part for creating this, the wafers or the coating, or so which step in the process?
Yeah, I think, like personally, I think this, for me, if you looked at these plates, the coated one that has little lines that protect the bonding surface, this colorful surface from the metal coating, and that is done with lithography. And we, couple of years, we didn't understand how to get rid of these little lines, and only like months ago we started like getting clean plates. And if you don't have clean plates, this process here, where you glue these, or not glue, but stack these plates on top of each other, as soon as you have a tiny particle in between from this lithography mask, it then deformed, it doesn't really stick anymore. There's a giant air bubble around it, around the particle, and that messes up the optical quality of this stack in the end. So that's like the last few years, my personal challenge, roughly. But that's just for me. There's more. Yeah. Otherwise, we wouldn't be 35 people. There would be just the engineers just figuring, okay, let's make another row, and then off we go. We actually, like lots of people from university, chemistry, physics, all the science together to make it work.